Today we're going to look at the describing data chapter. First, we're going to look at ways to present qualitative data graphically. A frequency table is a table with two columns. One column that lists the categories, the other for the frequencies with which the items in the categories occur. How many times or how many items fit into each category. So, an insurance company determines vehicle insurance premiums based on known risk factors. If a person is considered a higher risk, their premiums will be higher. One potential factor is the color of your car. The insurance company believes that people with some color cars are more likely to get into accidents. To research this, they examined police reports for recent total loss collisions. The data is summarized in the frequency table below. So looking at this, we have blue at a frequency of 25. Green had a frequency of 52. Red had a frequency of 41. White had a frequency of 36. Black had a frequency of 39. And gray had a frequency of 23. It's interesting that green has the highest frequency of collisions. I can speak from personal experience. I own a green car, and the number of accidents that I've almost gotten into because people don't see me is quite high. It has to do with the car blending in with the surrounding greenery, trees and whatnot. So a bar graph is a graph that displays a bar for each category with the length of each bar indicating the frequency of that category. So using our car data from above, note the highest frequency is 52, so our vertical axis needs to go from 0 to 52, but to keep it neat, we might as well go to 55. So we put a hash mark for every 5 units. So here we have our frequency. Here we have the colors of the car, and as you see, blue, that's 25. Green, and that looks like 52. And that's how this works. Another way to represent the same data that was in the previous table. Now, Pareto chart is a bar graph ordered from highest to lowest frequency. So here we've transferred our bar graph from earlier into a Pareto chart, and this is what we get. Again, it's the same information laid out in a different form. It's still a bar chart, but it's listed from the highest to the lowest. This way we know which has the highest frequency of total loss collisions. Example 4. In a survey, adults were asked whether they personally worried about a variety of environmental concerns. The numbers out of 1,012 survey who indicated that they worried a great deal about some selected concerns are summarized below. We have pollution of drinking water with a frequency of 597, contamination of soil and water by toxic waste, frequency of 526, air pollution with a frequency of 455, and global warming with a frequency of 354. Again, the data can be shown graphically in a bar graph, which we have here. Next up is the pie chart. A pie chart is a circle with wedges cut of varying sizes marked out like slices of pie or pizza. The relative sizes of the wedges corresponding to the relative frequencies of the categories. Pie charts can often benefit from including frequencies or relative frequencies, percents, in the chart next to the pie slices. Often having the category names next to the pie slices also makes the chart clearer. So here we have again, same information in a different fashion. We've used color to denote the different categories as well as labeling the categories and telling the number of accidents. pie chart itself gives us a nice visual representation, but without these numbers and names here, it would be a little more difficult to read. So those come in handy. Okay, the pie chart below shows the percentage of voters supporting each candidate running for a local Senate seat. If there are 20,000 voters in the district, the pie chart shows that about 11% of those, or about 2,200 voters, support Reeves. 11% and 11% of 20,000, which is what, 20,000 times 0.11, which is our 2,200. That's how that's calculated. So we can go from percentages to actual numbers if we know the total number of voters. Okay, a pictogram is a statistical graphic in which the size of the picture is intended to represent the frequencies or size of the values being represented. So a labor union might produce the graph below to show the difference between the average manager salary and the average worker salary. Looking at the picture, it would be reasonable to guess that the manager's salary is 4 times as large as the worker's salaries. The area of the big bag looks about 4 times as large. However, the manager's salaries are in fact only twice as large as the worker salaries, which is reflected by the manager bag being twice as tall. So this is one of the issues we have with statistics. This picture here doesn't tell us what represents the height or the size. In this case, the height. So it looks like this bag here is, like it says, about 4 times as big. However, it's only about twice as tall. And it doesn't state how it's represented, so it can be misleading. So here we have a couple of graphs. Compare the two graphs below, showing support for same-sex marriage rights from a poll taken in December 2008. The difference in the vertical scale on the first graph suggests a different story than the true differences in percentage. The second graph makes it look twice as many people oppose marriage as rights. So what we're doing here is we're showing ways that statistics, while the numbers are accurate, it can be made to look like it's not right. It's off. Or make it look worse than it is. So here we have a simple scale from 0 to 100. And we have what looks like about 45 and about 55. And that works. Now here the scale starts at 40. So going up, it actually looks more like 44. Oh yeah. This looks like 44%, and this would be 56%. So it's the same difference, but it looks like it's a whole lot more. It looks almost 3 times as much because of how the scale is done and how the frequency is started. So again, when we're representing statistical data, we have to be careful not to put it in a form that becomes misleading. And when looking at statistical representations, again, look for things like that, because statistics are often used to give false impressions. So a teacher records scores on a 20-point quiz for the 30 students in his class. The scores are, and here they are. So summarize these results in a frequency table by grouping like values. So we start off with 0, and we have what? 1, 2, 2 zeros. And then how many 5s do we have? 1, like 1 5, and 12. Do we have any 12s? There's 1 12, 15, 1, 2, 2 15s. I'm going to keep a running count here. 16, 1, 2 16s, 17. 1, 2, 3, 4 17s. 18. 1, 2, 3, 4, 5, 6, 7, 8 18s. 19. 1, 2, 3, 4 19s. 20. 1, 2, 3, 4, 5, 6. So that is 30 people. So that would be our frequency table. Now here's what the histogram for the values above would look like. Again, we have our frequency and we're starting at 0 and we're evenly spacing each frequency out so it doesn't look like it's different. This 8 is twice as, this 8 here is twice as long as this 4 here. Nothing is showing something that might be construed as different than it actually is. Now, since the scores are numerical values, this chart doesn't really make sense. The first and second bars are 5 values apart, while the later bars are only 1 value apart. It would be more correct to treat the horizontal axis as a number line, and this type of graph is called a histograph. The histogram is like a bar graph, but where the horizontal axis is a number line. So the values above a histogram would look like this, and you can see we have from 0, 2, 4, 6, all the way to 20, and we have a hash mark for 1 and 3 and 5. And you can see the group that had 0 is 2, and these groups that didn't have any scores are left at 0, and then all the other ones here. So now we're working with histograms. Another thing to consider is a class interval. Class intervals are groupings of data in general. We define class intervals so that each interval is equal in size. For example, if the first class contains values from 120 to 129, the second class would include values from 130 to 139. Typically, we try to have between 5 and 20 classes, depending upon the number of data we're working with. So let's see. Suppose we have collected weights from 100 male subjects as part of a nutrition study. For our weight data, we have values ranging from a low of 121 pounds to a high of 263 pounds, giving a total span of 263 minus 121 or 142. We could create 7 intervals with a width around 20, or 14 intervals with a width around 10, or somewhere in between. Oftentimes, we have to experiment with a few possibilities to find something that represents the data well. Let's try using an interval width of 15, and we could start at 121 or 120 since it's a nice rounded number. So we create our intervals, 120 to 134, 135, 149, and so forth. Then we have our frequencies. Frequencies here. And now we look at a bar or a histogram, and we see, again, everything's connecting. That's what a histogram does. The horizontal axis is a number line of some type. The only time you would not have these connecting is if there was no values, say, in here. So the data below come from a task in which the goal is to move a computer mouse to a target on the screen as fast as possible. On 20 of the trials, the target was a small rectangle. On the other 20, the target was a large rectangle. Time to reach the target was recorded on each trial. So again, we broke our intervals here. We're using intervals of 100, starting at 300. We have our frequencies on a small target and frequencies on a large target. One option to represent this data would be a comparative histogram or bar chart in which the bars for the small target group and large target group are placed next to each other, encoded by color. So there's that. But you could also use something called a frequency polygon. An alternative representation is a frequency polygon. A frequency polygon starts out like a histogram. We have our frequencies over here. We have our number line, which is reaction time in this case, here. But instead of drawing a bar, a point is placed in the midpoint of each interval at height equal to the frequency. Typically, the points are connected with a straight line to emphasize the distribution of the data. So we're putting the dots in the middle of the intervals, like this. And then we draw the connecting lines. And again, since we have two sets of data, they're color-coded, and if you look at this, this is easy to see the differences between the two sets of data. This here is kind of hard to look at. So again, it's depending on what you're displaying and how you want to display it to make it easier to read. In this case, the polygon is probably the easier way to go. So now we get to the work. The mean, also called the arithmetic mean, of a set of data is the sum of the data values divided by the number of values. So, you've probably heard of this and called it an average. We're going to call it a mean for right now. So Marcy's exam scores for her last math class were 79, 86, 82, 94. Find the mean of the exam scores. Now, mean of a sample is x with a bar over it. In other words, x bar. This equals the sum of all the values, which are x's, over n, which is the number of values. So essentially, I'm looking at x bar equals 79 plus 86 plus 82 plus 94 over 4. Okay, so let's add that up. Okay, and this becomes 341 over 4, which is 85.25. So that's the mean of those scores. Okay. Number of touchdown passes thrown by each of the 31 teams in the National Football League in the 2000 season are shown below. Find the average or mean number of touchdown passes. So again, our x bar is equal to the sum of all the x's over n. Well, we know n is 31. So let's add up all our values and see what we get. Lots of values here. I wonder some of those low numbers at the end, was this a shortened football season or something? I get 634. I'm going to go with that. I think I got them all right. Typically, we would add them twice to be sure. I get 20 point, I'm going to go 2 decimal places, 0.45. Okay, next up. 100 families in a particular neighborhood are asked their annual household income to the nearest $5,000. The results are summarized in a frequency table below. Find the mean household income. So, here's what we got going on here. Basically, we have a frequency of 6 at 15,000. So this would be 15 plus 15 plus 15 plus 15 plus 15 plus 15, which I believe equals 90. Another way to look at it, though, would be 6 times 15, which was 90. Here we have 8 times 20, which is 160. Here I have 11 times 25, which is what, 275? Here I have 17 times 30, which is 510. Here I have 19 times 35, which is 665. Here I have 20 times 40, which is 800. Here I have 12 times 45, which is what, 450 plus 90, or 540. And here I have 7 times 50, which is 350. And then I need to add all those up. 90 plus 160 plus 275 plus 510 plus 665 plus 800 plus 540 plus 350, and I get the sum of my x. It says there's 100 families, so n equals 100. So our x bar is equal to 3390 over 100, which is 33.9. And that's thousands. And that is our solution there. Simple enough. Okay, so let's take that one step further. What did we know? We knew our sum of x's was 3390 and our n was 100. Standing off the last example, suppose a new family moves into the neighborhood that has a household income of 5 million, which is 5,000 thousand. Add this to our sample and calculate the new mean household income. So we have the total we had for the first 100 of them, plus this new family. I guess that's Bill Gates' family. So this is our new total. And n is just 101. So our new x bar, our new mean, 8,390 over 101. And this is 83.07 thousand. So you see how just that one number can make a big difference. We're talking almost 50,000 difference. Just one person, one really large amount. So that brings us to our next concept, which is called the median. The median of a set of data is the value in the middle when the data is in order, typically from smallest to largest, but it can be done from largest to smallest as well. To find the median, begin by listing the data in order from smallest to largest or largest to smallest. The number of data values n is odd, then the median is the middle data value. This value can't be found by rounding n divided by 2 up to the next whole number. If the number of data values is even, there is no one middle value. So we find the mean of the two middle values n divided by 2 and the value n divided by 2 plus 1. So let's go back to our football touchdown data. List the data in order. It was already that way, so we're lucky. And let's find the median. Remember that n is 31. So n is 31. So to find the median, we take n divided by 2, which is 31 divided by 2, which is 15.5. Since it's not an even integer, we round up to 16. And our median is the 16th data point. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the median is 20. That's it. So now we have find the median of these quiz scores. So first we need to list it, and let's list it from lowest to highest. I see a 2 here. I see a 4. I see 2 5s. I see 1 6. 2 7s. 2 8s. 2 7s. 2 8s. And a 10. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So n divided by 2 equals 10 divided by 2, which is 5. So I need to find a fifth plus the sixth data point and divide that by 2. So 1, 2, 3, 4, 5, and 6. So this becomes 6 plus 7 divided by 2. 13 divided by 2, which is 6.5. It should be right in here. Now here's what the median does. The median splits the data into two equal parts. So let's look. Well, we have 5 data points here and 5 data points here. And the median would be 6.5 here. Okay, now this one gets a little more difficult. So we'll go back to our original household income data. We have our 100 data values. Since 100 is an even number, we need to find the mean of the two middle data values, the 50th and 51st value, to find the median income. So here's how we do this with the frequency table. Let's find the 50th, and 51st value. So what we can do is something called a cumulative frequency. And essentially what we're doing is we're adding up the totals of the frequencies. So here so far I've got my first 6 data points. I have 8 more here, so to this point there's 14. I have 11 more here, so at this point there's 25. I have 17 here. So at this point I have 42. And I have 19, so that gives me 61. So basically what we're saying is the 43rd, 44th, all the way to the 61st are in this section here. Which means that the 50th and the 51st are in there as well. So we have the 50th, which would be 35, plus the 51st, which would be 35, over 2. That's a 70 over 2, or 35. That would be the median. That's how we do it with a frequency table. Okay, the third thing we're looking at is something called the mode. The mode is an element of the data set that occurs most frequently. Going back to our vehicle color survey, we collected the following data. Identify the mode. So which one has the highest frequency? Looks like green. Okay. It is possible for a data set to have more than one mode if several categories have the same frequency, or no modes if every category only occurs once. Let's look at each employee's salary. Find the mode. So I have 48,800. Do I have another one of those? No. So there's only one of those. I have 42,000 here. Do I have another one of those? No. So there's only one of those. I have 40,500. Is that another one of those? 40,000. Nope. 39. Nope. 35. No. 30. Then 28. So they all only occur once. So that means there is no mode. If every data value occurs only once, there is no mode. If more than one value occurs more often than once, but the same amount, so if I have two values that occur twice and nothing else that occurs more than once, both those values would be the mode. Okay, the next concept we have here is something called the range. Essentially, the range is the difference between the maximum value and the minimum value of the data set. So let's look at these quiz scores. Find the range. Well, the minimum value is 71 and the maximum value is 98. So we have 98 minus 71, which is 27. And that's the range. Okay, going back to our employees again. Find the range. Well, we have our maximum value and our minimum value. 48,800 minus 28,500. We have 20,300. And that's the range. Okay, so next we get into the biggie. If you intend on going further in statistics, this is one that you will definitely want to know how to do. Standard deviation is a measure of variation based on measuring how far each data value deviates or is different from the mean. A few important characteristics. Standard deviation is always positive. Standard deviation will be 0 if all the data values are equal and will get larger as the data spreads out. So if the larger the range, the larger the standard deviation. Standard deviation has the same units as the original data, and standard deviation, like the mean, can be highly influenced by outliers. You've probably heard this term used when, seeing as how it's coming up to election season, when they do voter polls, they usually state what the standard deviation is. We're not going to get too deep in this. Basically, we're going to learn how to calculate it. So to compute standard deviation, find the deviation of each data from the mean. In other words, subtract the mean from the data value. Square each deviation. Add the squared deviations. Divide by n the number of data value if the data represents a whole population. Divide by n minus 1 if the data is from a sample. Compute the square root of the result. So, talking about a sample, standard deviation is denoted S equal to the square root of the sum of x minus x bar squared over n minus 1. That's for a sample. So now that's kind of difficult to work with. So here's how we set this up. This is my recommendation. An animal hospital recorded the following lifespans of selected dogs. So what we start with is we have our x values, which are 7, 9, 11, 15, 18, and 12. The first thing we want to do is find the deviation from the mean, so we need to find the mean. So what's our sum of x's? We add up our sum of x's. And we get 72. And we had n is equal to 6. So x bar is equal to 72 divided by 6, which is 12. So find the deviation of each data from the mean. Or subtract the mean from the data value. So I'm looking for x minus x bar. So this would be 7 minus 12, which is negative 5. This is 9 minus 12, which is negative 3. This is 11 minus 12, which is negative 1. This is 15 minus 12, which is 3. This is 18 minus 12, which is 6. This is 12 minus 12, which is 0. As I said, this is the easiest way to keep track of everything. So now it says square each deviation. So I'm looking for x minus x bar squared. So negative 5 squared is 25. Negative 3 squared is 9. Negative 1 squared is 1. 3 squared is 9. And 6 squared is 36. And 0 squared is 0. And I need the sum of that. Simply add those up. 25 plus 9 plus 1 plus 9 plus 36. And I get 80. Divide by, in this case, n minus 1. So I need 80 divided by 6 minus 1, which is 80 divided by 5, which is 16. And then compute the square root. So the square root of 16 is 4. So S is equal to 4. Guess we could say 4 years. Okay, the next thing we're going to talk about is quartiles. Quartiles are values that divide the data into quarters. The first quartile, Q1, is the value so that 25% of the data values are below it. The third quartile, Q3, is the value so that 75% of the data values are below it. And you probably guessed that the second quartile is the same as the median, since the median is the value so that 50% of the data values are below it. This will divide the data into quarters. 25% of the data in between the minimum and Q1, 25 in between Q1 and the median, 25% is between the median and Q3, and 25% is between Q3 and the maximum value. So here's what we have. The 5-number summary takes this form. You have the minimum, Q1, median, Q3, maximum. To compute the first quartile, begin by entering the data from smallest to largest. Compute the locator, which is L, the locator, equal to 0.25 times n, which is the number of data points. If L is a decimal value, round up to the next value, even if it's 0.001. So if it's, say, 4.001, you still round up to the 5th data point. Use the data in that position. If L is a whole number, find the mean of the day values and the Lth in the L plus 1 position. So it's just like to find a third quartile, use the same procedure as for Q1, but with a locator of L equals 0.75 n. So let's look at this. Suppose we have measured 9 females and their heights in inches, sorted from smallest to largest are, here they are, find the first quartile and the third quartile. So we have n equals 9. So for Q1, locator 1 is equal to n times 0.25, which is 9 times 0.25, which is 2.25. Let me double check that. Yeah. So that would mean the third data point, which would be 62. Okay, to find Q3, L3 is equal to n times 0.75, is 9 times 0.75, which is 6.75. So we would need the seventh data point, 3, 4, 5, 6, 7, which is 69. And that's it. Okay. So we have our 8 female heights in inches, sorted from smallest to largest. Find the first quartile and the third. These aren't the same, really the same problem, is it? Oh, they dropped one. Yes, they dropped the last one. So now n equals 8. So for Q1, the locator 1 is equal to 8 times 0.25, which is 2. So we need to take the average of the second and third. So I take 60, which is the second, with 62, which is the third, and divide by 2. 122 divided by 2, and we get 61 for Q1. So we take the second plus the third over 2. For Q3, we have L3 is 8 times 0.75, which is 6. So we take the 6th plus the 7th over 2, which is 67 plus 69 over 2, which is 69, not 68. 136 over 2, or 68. Okay, so for the 5 female sample, find the 5 number summary, or the 9 female sample. So let's just do this up here. What's my median? Median is n divided by 2, 9 divided by 2, which is 4.5. So we need the 5th data point, which is 1, 2, 3, 4, 5, 66. So my 5 number summary is we have a minimum, which is 59. Minimum of 59. Q1 was 62. We have a median, Q3, and a maximum. What was our median? 66. 66. Q3 was 69, and maximum was 72, I believe. Okay, same deal here. We had a min, Q1, a median, Q3, and a max. The max was 70. The min was 59. Q1 was 61 and Q3 was 68. Go back and find our median here. And the median of n divided by 2, which is 8 divided by 2 equals 4. So we want the fourth plus the fifth divided by 2. That's these two here. 64 plus 66 over 2, which is 130, divided by 2, which is 65. And our median is 65. Okay, the last thing we have to talk about is a box plot. Box plot is a graphical representation of a 5-number summary. To create a box plot, a number line is first drawn. A box is drawn from the first quartile to the third quartile, and a line is drawn through the box at the median. Whiskers are extended out to the minimum and maximum values. So this is what our box plot for the 9 female height data is. So here is our minimum value. We have a whisker out to that. Here is our maximum value. We have a whisker out to that. This is Q1 and this is Q3 and this is the median. So let's see if we can do this. 8 female heights video. Let's see, the minimum was 59 again, right? Q1, median, Q3, and the maximum was 70. Let's go back and see what everything else was. 61, 65, 68. 61, 65, 68. So first we draw our box from Q1 to Q3. I have 61 to 65. Then we draw our line up to 68. Sorry. Then we draw our line for the median at 65. Then we have our whisker to 70. And we have our other whisker to 59. And there's our box plot for that data. Okay, so we're going to look at and compare two box plots here. So the box plot of service times for 2 fast food restaurants is shown below. Store 1 and Store 2. The service time in minutes. So while Store 2 has a slightly shorter median service time, right here, 2.1 versus 2.3 minutes, Store 2 is less consistent with a wider spread of the data. At Store 1, 75% of customers were served within 2.9 minutes, while at Store 2, 75% of customers were served within 5.7 minutes. That's Q3 there. Which store would you go to in a hurry? Well, that depends on your opinion about luck. 25% of the customers at Store 2 had to wait 5.7 to 9.6 minutes. Or more to the point, 75% of the customers at Store 1 get in and out under 3 minutes. So again, it's a matter of how you look at it, what your goal is. Because while the average time here is lower, the spread is not as wide here. You may very well be the unlucky soul that has to wait 9.6 minutes. So that is the describing data chapter. Hope you guys have a good day, and I will talk to you next time.